Good morning, afternoon, or evening. How y'all doing today? Welcome back to Mr. Morrow's Honors Geometry class. Today we're going to continue with our circles. We learned a good theorem yesterday. Let's just go over it real quickly. When a radius is perpendicular to a chord, it bisects that chord. Vice versa, if a radius bisects a chord, then it is perpendicular to it. So basically, the radii is perpendicular bisector to chords, and that's very powerful. We're going to continue with chord and radius relationships, and today we're going to talk about the center-chord equidistant theorem. Basically states that if two chords of a circle are equidistant from each other, or from the center rather, sorry, then they are congruent. So what am I saying? This figure pretty much describes it, but let's put this into words. If OB is congruent to OE, so in other words, the distance from this chord to the center is congruent to this chord to the center. They're both congruent. They are equidistant from the center. It does not mean that they're equidistant from each other. That means that they're equidistant from the center. Then the chords will be congruent. So if chord AC and chord DF are equidistant to the center, making BO congruent to OE, then those two chords AC and DF are congruent. This is awesome stuff, really powerful. Helps you a lot with proofs and figuring out values. It's awesome. Yes, sir? No, that does not necessarily mean, well, that's a different theorem, right? Yes. If this radii is perpendicular here, right? So that means that this radii will cut this chord into halves, right? That was yesterday's theorem, correct? Very good, because it's perpendicular. Okay? And then we have vice versa. The converse of the center-chord equidistant theorem. If two chords of a circle are congruent, then they are equidistant from the center of the circle.
Teachers, please pardon the interruption. The following students need to report to the
Okay.
office at the time of their car key. The owner of a
So let me just pause during this and awesome. All right, boys, sorry about that. We had to pause there for a second. Okay, so the converse of the center-chord equidistant theorem states that if two chords of a circle are congruent, then they are equidistant from the center of the circle. Same, it's just the converse. So basically, if they tell you that chord AC is congruent to chord DF, then OB will be congruent to OE. So then this guy will be congruent to this guy. Then they are equidistant from the center. And that's literally the only two theorems we have to learn today. Okay? It's pretty awesome. Now, just to expand upon some things. Since this guy is perpendicular, okay?
One more time for the owner.
Give me 1 second, please. Okay, sorry about that. Okay, so just to expand upon this, since this OB is perpendicular to AC, that means it will actually bisect AC. Now, if I take a radii here, this guy is congruent to this guy. You have OB is congruent to itself. So you just created two congruent triangles. And I can do the same thing over here. And now I have four congruent triangles. Okay, so that's where this is all going. Okay, you got to know the relationships here because it's very important. And it can lead to really awesome quick calculations on an SAT problem and also quick calculations on any proofs. which are very important. Yes, sir, my brother.
Will you also be able to show this other triangle like the intersection of AB?
The triangle in between. Oh, okay. Okay, well, very good. You know that these two guys will be congruent, right? So all I can really say here is that this is an isosceles triangle. Now, I could drop a radii right here, correct? And then create an altitude here, and then go ahead and bisect this guy, and then yes, then I'll have another two congruent triangles. Does that make sense? That's a great question, son. Thank you. Well done. All right, boys. So let's get to it. Given, you have circle O here. AB is congruent to CD. So AB, which is the whole thing, is congruent to CD, which is the whole thing. OP is 2x minus 5, and OQ is 4x plus 19. I want you to find OP. Well, what you said them equal to each other, right? Because if AB is congruent to CD, then that means that PO is congruent to OQ because they're equidistant from the center. So 12x minus 5 will equal 4x plus 19. Subtract the 4x, that's 8x. Add the 5, that would be 24. So x would equal 3. But please be careful, guys. You know by now in geometry, it's not just finding the x. It's reading the problem. They want to find OP. So we got to plug that x into OP, which is 12 times 3 is 36 minus 5. So we have 31 and whatever units that would be. We don't know that theorem, though, guys. This becomes a very tedious situation. Very challenging. Pretty simple, though. It's easy, right? Really simple. Okay. May I continue, rather? Yeah? Easy, right? All right. Let's continue now to our proof. All right. I know. Your favorite. Another proof. Okay. Actually, let me go ahead and copy this. All right. Oh, okay. We could see it all there. Okay. So we have triangle ABC is isosceles with base AC. We have circle P rather. We know that PQ is perpendicular to AB and PR is perpendicular to CB. So we have a lot of really good information here. First off, AB is isosceles with base AC. Okay, that's awesome. If it's isosceles, what do we know about AB and BC? Right, well, I put the rest of the given. I really shouldn't have put the givens. We know that AB is congruent to BC because of definition of isosceles. Okay, that's awesome. So we know that AB is congruent to CB. I'm trying to prove that triangle PQR, I'll highlight it in blue, triangle PQR is isosceles as well. Okay? So if AB is congruent to BC, what do we know immediately about PQ and PR? They have to be congruent because of the converse of the center-chord equidistant theorem. Very good, my brother. Now, some of you may say, but wait a second, Mr. Morrow, what about the PQ being perpendicular to AB and the PR being perpendicular to CB? That was just extra information. Could I have said that bisects AB and that bisects CB? Sure, I could have. Would it have helped with our proof, though? No. Now that we have proven that PQ is congruent to PR, that's it. It's an isosceles triangle. Definition of isosceles. So they just gave us extra information that we really did not need. Yes, sir, my brother. PRQ is congruent to PQR. Um, I guess, but I mean, that would have been a lot longer, right? You would have first had to said, okay, PQA and PRC are congruent because right angles are congruent. Then you would have still had to say that PR and that PQ are congruent. But because then you would have said that angle PQR and PRQ are congruent because of sides and angles. That's the only way you would have done that. But you wouldn't have been able to say subtraction property to prove that PQR and angle PRQ are congruent just because of the 90. No. No. Does that make sense, son? Thank you, my brother. And why would you want to convolute things? You know that if those chords are congruent, they're equidistant from each other right off the bat. Does that make sense? All right, boys, that's literally it. We're done. So let's get to work. Hope you learned a lot. Have a great day, and thank you very much.